Good morning, everybody. I hope you had a good weekend. And we'll continue with our hypothesis testing. We have done hypothesis testing last time for population proportion. And we are going to do hypothesis testing for population mean today, as well as population standard deviation, if time permits. So let's get to the acronym that we have been using. PMS, proportion, mean, and standard deviation, PMS. Now, we are going to, we have done the hypothesis testing for proportion. Now we are going to do hypothesis testing for mean. However, when we do hypothesis testing for mean, there are two scenarios that we need to consider. One is when we know sigma. Sigma is the population standard deviation. And the other is when you don't know sigma. That means you do not know population standard deviation. If you know sigma, you use z-scores table. On the other hand, if you do not know sigma, you use student t-distribution table. Okay, so this is the structure. And for population standard deviation, which we will be testing actually for variance, we are going to be using chi-square distribution. Okay, so this is what it is. And for proportion, we already did it. As you know, we had to ensure the normality condition. Then we used the central limit theorem for proportion, which basically we needed to make sure NP is greater than or equal to 10, and NQ, where Q is 1 minus P, is greater than or equal to 10. So this is the tree diagram for hypothesis testing. And of course, exact similar tree diagram for population proportion, I mean, not proportion, confidence interval. We did confidence interval for population proportion, mean, and standard deviation. Structure is exactly the same and similar kind of distributions. So when we didn't know sigma, we used t-distribution. When we knew sigma, we use z-scores. Okay, for proportion, we use z-scores table as well. We just needed to make sure that the normality condition is satisfied. And then for standard deviation, confidence interval for standard deviation, we use chi-square distribution. Okay, so this is what the structure is. Now for today's lecture, what I'm going to do, I'm going to go ahead and probably talk about this plus this, I think. Okay, I don't think we will have time to start that. So be prepared for this and that. That means hypothesis testing for mean when you know sigma, and hypothesis testing for mean when you do not know sigma. By the way, in reality, this is what people use in the real world. A lot of the times we use t-distribution. That means we really don't know population standard deviation in many cases. Therefore, we end up using student t-distribution. Okay. Any question before I get started? Anybody? Any question? Anyone? No? Okay. Let's bring back the screen. Is everybody okay with hypothesis testing for population proportion? Any question? Anybody has any difficulties with any of the problems? Okay. So we are going to go ahead and start hypothesis testing for mean. The first case is when we do know sigma. That means we know the population standard deviation. The first scenario is that when we know population standard deviation. Now, again, we are going to go through the steps here. So let me go ahead and give you an outline or overview of what the steps involve. So requirements is sigma known, okay? And we do simple random sampling, which means that we do sampling completely randomly without any bias or prejudice. And population is normally distributed, and our sample size is greater than or equal to 30, okay? Sample size is greater than or equal to 30. So somehow we have to know sigma, as well as we have to make sure that the population is normally distributed, or make sure that the sample size is bigger than or equal to 30. Then we will be doing null and alternative hypothesis. Remember, null hypothesis always includes the equality. However, what I did not put here is this. Sometimes null could be mu is less than or equal to mu naught, some value, or it could be mu is greater than or equal to mu naught. And also it could be mu is equal to mu naught. All three include equality, even though I just put here one case, but all three are possibilities. So if this is the case you're dealing with, your alternative, so these are your null hypothesis, because it includes the equality. However, if you're considering, let's say, one by one, so number one here, mu is less than or equal to mu naught, where mu naught is some fixed value, okay? Your complement is going to be mu is greater than mu naught. In this case, number two, mu is greater than or equal to mu naught. That is your null hypothesis. Your complement is going to be mu is less than mu naught. And number three, mu is equal to mu naught. In that case, your complement is going to be mu is not equal to mu naught. Look, all of these are alternative hypotheses. They do not include equalities. Now, test statistic Z, this has a normal distribution with mean 0, standard deviation 1. So distribution of this, so x bar minus mu over sigma divided by square root of n. This has a distribution which is normal with a mean of 0, standard deviation of 1. That is to say, it has the standard normal distribution. All right, so that's your z-score. I mean test statistic, what we call, or I call rather, z star. Now you need to find the critical values, okay, determined by the significance level alpha. For right tail test, the statistic z is greater than or equal to z sub alpha, some value. Z is less than or equal to negative z sub alpha for left tail. And for both tail, z is greater than or equal to z sub alpha over 2. That's what it is. So now conclusion, we do our conclusion in two different ways. One is critical region method and test statistic. Basically, you take the test statistic and see whether it falls within the critical region or not. If it falls in the critical region, then you reject the null hypothesis. If it does not fall in the critical region, you do not reject the null hypothesis. And p-value, which is another way of finding the conclusion, basically it stands for probability value or p-value. It tells you whether you reject the null hypothesis or you don't. So you will reject the null hypothesis if your p-value is greater than alpha or alpha over 2, depending on how many tails we are considering. For single tail, p-value is alpha greater than alpha. So that, sorry, if p-value is greater than alpha, you do not reject. Sorry, do not reject. On the other hand, p-value greater than or equal to alpha, p-value less than alpha, you do reject. And on the other hand, this is for single tail. On the other hand, if you do it for multiple tails, which is 2 tails, of course, you don't have more than 2. So the relation becomes p-value is greater than or equal to alpha over 2, okay? Rejection, do not reject, and p-value less than alpha over 2, do reject. So these are the things. And as I said previously, that in the real world, you will not be doing all these calculations by hand, even though I make you do it by hand in the class, because I want you to learn the logistics of it and make sure that you understand what you are doing, what calculations you are performing, and how it relates to the problem. However, in the real world, what you will do, you will basically input all of your data with your significance level and all the other information, and the program will give you an output, typically p-value. From that p-value and alpha relationship, you can either reject or you do not reject. That's what it is, okay? So this is the general structure again. This is the same process that we have followed to do hypothesis testing for population proportion. And this is the same process we will be doing for hypothesis testing for population mean, as well as for population standard deviation. Now, let's do one of the solved problems first. Okay, so this is something easy. According to textrequest.com, an American between 18 and 24 sends and receives about 128 text messages per day. So this is a data, national data. So this is kind of like mu that we are expecting. Assume that the population standard deviation is 20. So this is sigma. So let me identify sigma. Oops, not alpha. Sigma is equal to 20. Population standard deviation is 20 for this age group. To test this, you take a survey of 100 adults. So that's your N is equal to 100. In that age group, and find that their average is 120. So that's your X bar. So this 120 you got from a survey of 100 people. And the average of those 100 people is 120. So this should be your X bar is 120. At 0.025 significance level, test the claim that the average number of text messages a young adult sends is less than 128. Average number of text messages that they send is less than 128. So mu is less than 128. Mu is less than 128. So this, by the way, should be your alternative hypothesis because it does not have the equality sign. Okay? It does not have the equality sign. All right? So requirements. Do we know sigma? Yes, we do know sigma. All right. Sigma is 20. It's given in the problem. Our sample size N is equal to 100, which is greater than or equal to 30. It is actually not strictly greater than, but rather greater than or equal to. So the sampling distribution is bell-shaped or normal. So this sample size of 100 ensures that the sampling distribution of the sample means is bell-shaped. Now the null hypothesis is that mu is equal to 128. Technically, we could make it mu is greater than or equal to 128. Why? Because we are testing for less than. So if mu is greater than or equal to 128, it's not a problem. So mu is greater than or equal to 128, but I will not penalize you if you put equal, okay? And your alternative is mu is less than 128. Now your test statistic Z star is X bar minus mu divided by sigma over square root of n. Now here, keep in mind, people get confused with what is X bar and what is mu. Mu is about the entire population, whereas X bar is about a sample. See, we got this X bar of 120 from a sample of 100. We got the X bar of 120 from a sample of 100. Okay, so in our case, X bar is 120 and mu is 128. And also you can look at the null hypothesis. What does it equal to, or potentially what could it equal to, which is 128, all right? So that's your mu. Divided by sigma, sigma is 20, okay? Sigma is 20 divided by the square root of 100, and is the sample size. If you plug in all these numbers, you get Z star is equal to -4. Now, let's draw the bell-shaped curve. Mu is equal to 0 and sigma is equal to 1. Mu is equal to 0 and sigma is equal to 1. All right. Now, we are doing a single tail test because it's less than. Remember, alternative is less than. Single tail. Less than means left tail test. Greater than means right tail test. So it's less than. All right. Less than. So the significance level is 0.025. 0.025. Okay. And that gives you this value, -1.96. Now, how do you find this value? You have to know it. You should know it by now because I have gone through this many, many times over the last month or so. Okay, or at least 3 weeks, maybe more, no month. You go to the standard normal distribution table, you look inside the table, not in the first column or top row. You look inside the table, inside the table, and you find the value that is closest to 0.025. As a matter of fact, there is an exact value of 0.025, and that corresponds to -1.96. So your critical region, this is your critical region, which is from -1.96 to negative infinity. So from here all the way to negative infinity, which is here. Now your test statistic Z star is equal to -4, which of course falls in the critical region. So -4, -1.96 is right here. -4 probably would be somewhere here. So it does fall in the critical region. Since the test statistic Z star is equal to -4, falls within the critical region, which is -infinity to -1.96, we do reject the null hypothesis that mu is 28 or mu is greater than or equal to 128. Mu is greater than or equal to 128. That's what it is. And this is how you do the hypothesis testing for mean when you know sigma. This is what you should do. This is the process that you would follow for every single problem. Now, the p-value thing, so p-value, look, our alpha is equal to 0.025. Now, area to the left of this point is 0.025, but look, -4 is right here. So the area to the left of that is going to be smaller than 0.025, right? It's going to be smaller than 0.025. So p-value is less than alpha, which is 0.025. Because if you start from here, -1.96, area to the left, you have some area to the left, but if you start at -4, the area from there on will be less than the area if you were to start from -1.96. So you're talking about this chunk versus this whole chunk. Okay, this chunk is obviously smaller than this chunk. That means p-value is less than alpha or 0.025, meaning that we are going to reject the null hypothesis, reject H naught, that mu is greater than or equal to 128. So based on your calculations, you are claiming that mu is probably less than 128, okay? And what kind of confidence level you have in your calculation? You have about 2.5% chance that you might be wrong, which means you have 97.5% chance that you might be correct in your calculation. All right. So that's how you'll do it. Any question on this problem, anybody? If you understood this problem, you pretty much understood all the problems for this category. All right, as I have been telling you, if you understand one or two problems or one problem, not even two, the process is extremely similar. You just apply it to different scenarios or different conditions. Now that I have done this, we can do this problem before that. So let's go in reverse order today. So this problem says, according to, so let's bring it down here. I'm going to use this space to work on the problem. According to USA Today College, an American college student studies about 17 hours. So right away, you should be thinking an American college student. It's not coming from 20 college students or 30 college students. This average is coming from the nation or nationwide survey. So that's your mu is equal to 17. So 17 hours per week with population standard deviation 4 hours. So that tells you sigma is equal to 4. Okay. You'd like to know if a similar trend is present at your school. So you surveyed how many students? 100. So your n is equal to 100, which is greater than or equal to 30. So right away, normality condition you can think. Surveyed 100 students and found that their weekly average is 15 hours. So this is your X bar. Your X bar is 15. Remember, X bar or the sample mean, it always comes from the sample, okay? So this 15, you found it from this sample of 100 students. So now this time you're testing 10% significance level. Test the claim that the average number of hours students spend studying at your institution is less than 17. So less than 17, meaning mu is less than 17. That right away should give you a hint that this is your alternative hypothesis. This is your alternative hypothesis. That's what it means, okay? So as you read the problem, you can see that you can extract all the information that you need. You can extract all the information that you need, and then you can start working on the problem. So let's do step one. In step one, what we are going to do, we are going to make sure that we know sigma. Sigma is, where is sigma? Which is 4. Your sample size n is equal to 100, which is greater than or equal to 30. So normality condition satisfied. Normality satisfied. Number 2, your null and alternative hypothesis. Your null hypothesis H0 is mu is greater than or equal to 17. How do you get it? Or where do you get it from? See, if you're testing for less than, okay, so your alternative, null and alternative are always complements. So mu is greater than or equal to 17 because you're testing for less than. So your alternative is going to be mu is less than 17. Now, this should give you an idea about the number of tails that you're going to be using for hypothesis testing. It's less than meaning one tail. Which tail is it? Left tail. You do both tail only if your alternative is mu is not equal to some mu naught, some other value. So that's your alternative. When you have this, that's when you're gonna say, oh, okay, we're gonna do both tail test. Step number 3, your test statistic, Z star is gonna be X bar minus mu over sigma divided by square root of the sample size, which you do have already. X bar is 15 minus mu is 17. Mu could be equal to 17, right? Divided by sigma, which is 4, divided by, so sigma is 4, square root of the sample size, which is 100. If you do the math, it's not hard. 15 minus 17 is -2. Then 4 divided by square root of 100 is 10. So there's going to be -2 times you flip the bottom number, 10 over 4. So -2 times 10 is -20 divided by 4 is -5. So your Z star is equal to -5. So this is a number you may want to remember. Now step 4 is going to be creating the diagram and finding the critical region. So this is a standard normal distribution that we are dealing with. We are dealing with standard normal distribution. Now, look, we are doing left tail test because mu is less than 17. Now, what is the significance level, which is here? Alpha is equal to 0.10. All right. Now, this is the point you're interested in, and the area to the left of that point should be 0.10. That is your alpha. Now, associated with an area of 0.10, you will see it is -1.28. Now, this is something we have done so many times in the past. I expect you to be able to do it. Even in the last problem, I mentioned that you don't look for 0.10 on the first column or first row. You go inside the table and you try to find the value that is closest to 0.10, which I even remember is 1.003. That's the closest value to 0.10. And that value, associated with that value, there will be a Z-score. That means you go along the row and along the column to find out the values, and that is negative 1.28. So that's what your critical region. Your critical region is from negative infinity to negative 1.28, which is nothing but this. Everything from here to negative infinity, all right? Now, in step number 5, you take your test statistic, negative 5, and compare it against the critical region. Does it fall within the critical region? As it turns out that it does. So negative 1.28, which is right here, negative 5 is going to be probably somewhere here. So that's where negative 5 is. So it does fall in the critical region. Z star or test statistic, negative 5 falls within the critical region. Okay, within the critical region, which is negative infinity to negative 1.28. Therefore, I do reject the null hypothesis. That mu is greater than or equal to 17. Of course, you do reject the null hypothesis for the population under consideration for you, right? You are comparing national average versus your college's average. So your population, you reject the null hypothesis that mu is greater than or equal to 17 only for your student body, okay? Because that's what you are doing the calculation for. And folks, this is exactly how you'll do it. The same thing, same process again and again. And I will be doing the same thing again and again, 2 more times probably. We have 2 more problems here. So anybody has any question in this process? Anyone has any concern, questions? Okay. So let's clean up the screen. So we did this problem. Now let's go and do the next one, which is this. According to Pew Research Center, on the average, an American reads 12 books per year. Let's assume that the population standard deviation is 3. So your sigma is 3. Sigma is 3. For some reason, I keep writing alpha for sigma today. And this is your mu. You surveyed how many people? 40. That's your n is equal to 40. Oops, mu is equal to 12. So your n is equal to 40. So you surveyed 40 people in your city and found that their average was 9 books. So this is your x bar is equal to 9 because it came from your survey of 40 people. At 0.05 significance level, test the claim that the average number of books read by a typical American per year is less than 12. So it is less than 12. So mu is less than 12. Okay. So you're going to be testing that. Now, as you read the problem, you kind of extracted all the information. But what you are doing here, forget about all this language here. People read 12 books per year in the US. That's what Pew Research tells. On the average, that's what people read. But does it work for my city or for my community? So that's what you're trying to do. You kind of go out and survey people and see your average with the national average and make some conclusions. That's what you are trying to do. Once again, we are going to go to those 5 or 6 steps. Number 1, sigma known. So sigma is given to be 3. Your n sample size, which is 40, not 4, 40, obviously that is greater than or equal to 30. So normality condition is satisfied. Number 2, your null hypothesis and your alternative hypothesis. Your alternative hypothesis is that you are testing less than 12. Remember, alternative hypothesis never ever includes the equality, whereas null hypothesis always includes the equality, and it does help you find that. All right. Okay. So mu is less than 12. So your null is going to be complement of that. Mu is greater than or equal to 12. That's your null and alternative hypothesis. Step number 3, you test statistic Z star, which is x bar minus mu divided by sigma over square root of the sample size. And we plug in these values. X bar is 9 minus mu is 12 divided by sigma is 3 divided by square root of the sample size means square root of 40. So 9 minus 12 is negative 3 divided by 3 over square root of 40, which becomes negative 3 times square root of 40. You're going to flip it, right? The bottom 3. Now 3 and 3 cancel. That gives you negative square root of 40. And that value comes out to, so let's find it. 6.32. It's going to be negative 6.32. So your Z star value is going to be negative 6.32. And that's what you are calculating. So your Z star, you found it. Now, next, step 4, we are going to find the critical regions, okay? What I call critical region, CR. So you look at the bell-shaped curve, and this is 0, and this is 1. And what is my alpha? There should be alpha somewhere, 0.05, right? So your alpha is 0.05. We are doing left tail test, so this is going to be my 0.05, which you can look it up. It is negative 1.645, negative 1.645. So your critical region, it becomes from negative infinity to negative 1.645, which in essence is this region from here all the way to negative infinity. Now step number 5. Okay, your conclusion based on the test statistic and your critical region. So Z star, negative 6.32. So negative 1.645 is here. Negative 6 is probably somewhere here, right? Negative 6.32. So it does fall in the critical region. Remember, whenever your test statistic falls in the critical region, you do reject the null hypothesis. Okay, you do reject the null hypothesis. So we are going to write test statistic. It is statistic, not statistics. Test statistic Z star is equal to negative 6.32 falls in the critical region, negative infinity to negative 1.645. Hence, I reject the null hypothesis that mu is greater than or equal to 12. That's what your conclusion is. Now, if you want to do the p-value, again, remember all this normal distribution in theory, it goes to infinity, okay? Even though it falls off extremely quickly. So 0.05 is the area starting from here to the left, but p-value is going to be area starting from here to the left. So now p-value does not include anything to the right, okay? So therefore p-value is smaller than alpha. Alpha is 0.05, so p-value is smaller than alpha. So p-value would be all the area from here all the way to the left, okay, to the infinity negative. Whereas alpha is all the area starting from here. Obviously, p-value is less than alpha, in our case, 0.05. If p-value is less than alpha, okay, we don't know exactly what the p-value is, but from this diagram, we can see that it's going to be less than alpha. P-value less than alpha is equal to 0.05. Therefore, we do reject the null hypothesis. Mu is greater than or equal to 12. And that is the whole story. That is exactly what you will be doing. Any question on this problem, anybody? No questions, everybody okay?
No
All right.
questions.
Yes.
No questions.
Oh, no questions, okay. All right, the last problem from this group is this. Our friend, Mr. Zuckerberg, the founder of Facebook, recently, that is not recent anymore. I made this problem many years ago. So it could be 7 years old, who knows, maybe more, 10 years. Recently announced that an average person spends 50 minutes. So that is kind of like mu. Mu is 50. He probably has done some research or at least some Googling to figure out how much time people are spending on social media. So that's kind of like his notion of average for the entire country. So average person spends about 50 minutes per day on social media, which is Facebook, Instagram, and Messenger. When I made this, I don't think TikTok existed. I don't think, what is the other one? Snapchat. It didn't exist probably then. So in general, social media. Assume that the times spent on these social networks are normally distributed. So they kind of give it out to you. It's normally distributed. with population standard deviation 20. So your sigma is equal to 20. To test the claim, so test the claim at significance level 0.05. So that means your alpha is equal to 0.05. That the population mean is different from 50 minutes. So this is where you should get your clue about null hypothesis and alternative hypothesis. Then the population mean, sigma, I mean mu is the symbol for population mean, you already know, right? Mu is different from 50. That means mu is not equal to 50. Okay, so at 0.05 significance level, you need to test that average number of minutes people spend on social media is different than 50 minutes per day based on your survey of how many people? 200 people. That means n is equal to 200. That yielded an average of 40 minutes. So x bar is equal to 40. So you asked 200 people and then you found their average, and that average is 40. So that's your x bar. So please make sure that you know how to identify these different parts or different components of the problem as you read through the problem and as you structure the problem. So our solution becomes reasonably easy once we do that, okay? So step number 1 is this. Where am I? Okay, sigma, which is 20, and your n is equal to 200, which is way greater than 30, right? So normality condition is satisfied, check. Number 2, your null and alternative hypothesis H naught and H sub A. And from the problem wording, you got the H sub A, that mu is different than 50. That means is not equal to 50. That doesn't leave you with many choices, but mu is equal to 50. That's your 2, step number 2. Step number 3, you calculate the test statistic Z star, which is gonna be x bar minus mu divided by sigma over square root of the sample size, which will give you x bar is, by the way, we found it to be 40. So 40, remember, x bar always comes from the sample. It always comes from the sample, not from the population. From the wording of the problem, you will see it says an average person spends 50 minutes. So it doesn't say that is the average of 20 people or 40 people or 200 people. You know, it could be anything, just general statement. So normally population parameter is a general statement about the population. So 40 minus 50, all of it divided by sigma. Sigma is 20 divided by square root of sample size, which is 200. So 40 minus 50 is negative 10 times this. If I flip this, bottom is going to be square root of 200 divided by 20. So 10 goes into 22 times, is going to give me negative square root of 200. I'm going to do something different here slightly. 2 is the same as square root of 4, right? So it's going to be negative square root of 200 divided by 4, that is negative square root of 50. Okay, so now square root of 50, what value is it? 7.07. So your Z star is equal to negative 7.07. Z star is negative 7.07. So step number 4, we're going to do the critical regions, CR, critical regions. So Are we doing one tail test or two tail? Here we are doing two tail test. So we have to take alpha and divide it by 2. So alpha is equal to 0.05. So alpha over 2 is going to be 0.025. Remember, this alpha has to be divided between the two tails. So the right tail is going to be 0.025 and the left tail is going to be 0.025. Now, as you know from your past knowledge that it is negative 1.96 here and positive 1.96 associated with area of 0.025. Then your critical regions become this. Your critical regions are from here all the way to negative infinity, and from here all the way to positive infinity. Now, if I write it out in the form of interval, so my critical regions are going to be from negative infinity to negative 1.96, which is the left side, right? Union, right side, right highlighted region, 1.96 to positive infinity. All right. Now, step number 5, my test statistic Z star negative 7.7, negative 7.07, it obviously does not fall in the right side. So it's not on the right side because all the values on the right side are positive. It's a negative value. So it is possible that it will fall on the left interval, okay, or left critical region. As it turns out, it does. So negative 1.96 is right here. So negative 7.07 is probably somewhere around there. So it does fall in the critical region. So test statistic Z star is equal to negative 7.07 falls in the critical region. Which one? Negative infinity to negative 1.96. Remember, for this particular problem, because of two tails, we have two critical regions, one associated with the left and one associated with the right. So our test statistic falls in the left critical region. Maybe I should use the word left here. Left critical region. Therefore, I reject the null hypothesis H dot that mu is equal to 50. And step number 6, you can do the p-value method. Now, once again, normal distribution curve falls off very quickly, but it does in theory go up to negative infinity and positive infinity. Obviously, the area of 0.025, it starts from negative 1.96 onwards or backwards to the left to negative infinity. And p-value, however, is going to start right here from negative 7.07 from this point towards negative infinity. So this 0.05 includes the area starting from negative 7.07. Therefore, p-value, that means the area associated with z-score, test statistic of negative 7.07 is less than alpha, which is 0.025. Therefore, I reject the null hypothesis that what? Mu is equal to 50. I reject the null hypothesis that mu is equal to 50. And that is the whole story, guys. I have done 4 different problems for hypothesis testing. 4 different problems for hypothesis testing where you know the population standard deviation sigma. And if you understood one problem, the rest were basically repetition of the same problem or same process, only with different numbers. And I think if you did follow me, you should have gotten the process pretty well crafted by now. Okay, this is a very standard process that one goes through for hypothesis testing, and you should be comfortable with it. Any question, anybody? No questions? Okay, good. Okay, I just realized that, can you guys hear me? Nobody was saying anything. I just realized that I was muted all this time. Just the last couple of minutes. Actually, gosh, 6 minutes. I didn't even realize. Nobody said anything. Okay, I don't know. That makes me wonder if people are paying attention. Okay, let's go ahead and work on the problem again. I'm gonna go back and talk about this again, because I think I may have missed it. So the whole process is the same, okay? The whole process for doing hypothesis testing for population mean when you do not know sigma is exactly the same, except instead of z-scores or standard normal distribution, you use t-distribution, which is this. Now, I'll write it down side by side so that you can see the difference. For Z star, the formula was x bar minus mu divided by sigma over square root of the sample size. And for T distribution or T star test statistic, is exactly the same, x bar minus mu divided by, now you do not know sigma, so you replace it with sample standard deviation S, which you also divide by square root of the sample size. And the difference between standard normal distribution, let's call it standard normal distribution like this, and the t-distribution is a bit stretched out, okay? It's a bit flattened to the right and to the left, okay? Now, what you do is this. You use t-distribution when you do not know sigma. And the main difference is that you replace sigma with the sample standard deviation. And as the sample size increases, what happens is that this t-distribution, which is kind of stretched to the right in both directions, starts to look more and more like normal distribution. And the process is pretty much the same, everything else. So let's go ahead and work on the first problem. You'd like to test the claim that an ordinary egg field worker in Salinas, California makes $15,000 per year, okay? A boundary for federal poverty level, and which I think is different now because I made the problem a while ago. So you take a random sample of 10 field workers and find the following numbers, okay? You find the following numbers. So now, also make the assumption that distribution of incomes for the field workers is bell-shaped or normal. At 0.05 significance level, test the claim that the average income for the field workers is different than 15,000. Average income for the field workers is different than 15,000. So let's go ahead and go through the steps here. Requirements. It says that it's approximately bell-shaped or normally distributed. So normality condition could be assumed somewhat. Now you're testing whether it's different than 15,000. So mu is not equal to 15,000. That's your alternative. Sorry, this should be a alternative hypothesis. And mu is equal to 15,000. That should be your null hypothesis. Now, in step number 3, you calculate the test statistics. X bar is the average of these numbers, which, by the way, is 17,340. X bar is the average of these numbers. It is 17,340. And mu is 15,000, which is this. And standard deviation is this. Standard deviation for these numbers is 3514.79, and square root of n is the sample size, which is 10. Okay, so that is your n is equal to 10. And if you do the calculations, you get T star is equal to 2.11. So that's a value you need to keep in mind. T star is equal to 2.11. Now, in the next step, what we are going to do, we are going to go ahead and do the calculation for critical regions, okay? And give me a second, let me pull the table here. Let's see, where is my table? Okay, I found my table. You guys have the table, I sent it to you as well. All right, so we are gonna go ahead and look at the table. Now, let's go ahead and find the critical regions. So this is gonna be like this. So this is 0. Now we are doing a two-tail test because mu is not equal to 15,000. That's what we are testing. So now our significance level alpha is equal to 0.05. So alpha over 2 is 0.025. So in our case, area in two tails is going to be 0.05. So 0.025, and this is 0.025, okay? 0.025. So now you look it up from the table, okay? You look it up in the table. So area in one tail versus area in two tails, okay? In our case, area in two tails, all right? So area in two tails is gonna be 0.05. So we look at that, and our degree of freedom, df, is n minus 1, which is 10 minus 1, that is 9. So if we look at the row labeled 9 and area in two tail 0.05, it is going to be 2.262. Oh, I already have it here. I forgot to look here. And negative 2.262. So my critical region in essence becomes everything from this point, okay? Everything from this point to negative infinity, everything from this point to positive infinity. So the critical region is, so this is my critical region. Critical region is from negative infinity to negative 2.262 and 2.262 to positive infinity. Now 2.11, where does it fall? 2.11 is a positive number, so obviously it's not going to be on the left side or on the left critical region. It could be on the right critical region, but 2.11, and this is 2.262. So it really doesn't fall in the critical region. It's 2.11. It's right before the critical region. So your test statistic T star 2.11 does not fall within the critical regions, either left or the right. So we fail to reject the null hypothesis that the average income for the field workers is 15,000. We fail to reject the null hypothesis that the average income for the field workers is 15,000. So that's how you will do it. Any question, anybody? Anyone has any question? Araceli, any question about this problem?
No, so far I'm good. Thank you.
Okay. All right. My microphone was muted before and nobody said anything. I was writing and talking. So now, can anybody volunteer to find the standard deviation and the mean for these data sets? There are 3 data sets for which I need the mean and the standard deviation. Is there anybody willing to volunteer? Just find the standard deviation. That will save me a little bit of time. And it'll give you a little bit of practice. Anybody? Any volunteer? I need 3 volunteers. Nobody wants to volunteer. All right. In that case, I'll volunteer myself again. All right. So the next problem, you'd like to know how much time on the average a student spends per day on Facebook. So you asked 15 randomly selected students and get the following data in minutes. Assuming normality and based on your data collection, can you test the claim that mean amount of time students spends on Facebook is less than 30 minutes per day at 0.05 significance level? So less than 30, all right? So let's extract the information. So this is your alpha. There's mu, okay? You're testing mu less than 30, okay? So that's your alternative hypothesis. And null is gonna be mu is greater than or equal to 30. And n is 15, n is equal to 15. And we also need x bar, okay, and s. These 2 numbers we are going to get from these data points. And let me calculate it right now. So give me a minute or so. As it turns out that I have the data in my calculator, so I can go ahead and quickly calculate it. So it should not be a problem at all. Second 6 is going to give me L6. That's where the data is. Okay. For this data set, X bar is 44. And the sample standard deviation is 19.89. 19.89. So now we are going to go ahead and do the problem. So number 1, normality, approximately normal, is given in the problem. Approximately bell-shaped. Given, okay? The problem says that. Number 2 is this. Your test statistic, T star, is going to be X bar minus mu divided by S over square root of the sample size. X bar is 44 minus mu is 30, right? You're testing 30. Oh, I forgot something. Nobody said anything. Number 2, this is number 3. Null and alternative hypothesis, right? Null and alternative. So you're testing that on Facebook less than 30 minutes, okay? Less than 30 minutes. So mu is less than 30, whereas mu is greater than or equal to 30. So that's what the null and alternative hypothesis. Remember, we got that from the problem statement, okay? The mean amount of time students spends on Facebook is less than 30 minutes per day, okay? Less than, so mu is less than 30. So that does not include the equality. Therefore, it should be the alternative hypothesis. And complement of that is mu is greater than or equal to 30. That is the null hypothesis. So X bar is 44, mu is 30, divided by standard deviation is 19.89, divided by square root of the sample size, and you surveyed 15 people. And that is going to give you 40 minus 30, 44 minus 30 is 14, divided by 19.89 times square root of 15. And if you do that calculation, you should get, so let's do the calculation myself. 15 times 14 divided by 19.89, that is 2.72. 2.72. Your test statistic T star is equal to 2.72. That's what your test statistic is. So that's step number 3. Now step number 4, the critical regions. So we are gonna draw a sort of stretched out bell shape, means 0, okay? And we are gonna have to look at area in one tail alpha. So area in one tail 0.05. That's what we are looking for. And area in two tail is gonna be 0.10. So that gives me the following. We will also have to consider the degrees of freedom df, which is n minus 1, that is 15 minus 1 is equal to 14. So your degrees of freedom is 14, and you look it up in the t distribution table, critical values for t, okay? So this is the point we are looking for. We have to make sure that we look at row label 14, and area in one tail is 0.05. Okay, in our case, area in one tail on the top, you'll be looking at area in one tail 0.05, and degrees of freedom 14. That gives you 1.761 negative. Okay, negative 1.761. So your critical regions is gonna be from negative infinity to negative 1.761, which in essence is this region from here all the way to negative infinity. And this is what I put in this here. Okay. Next, step number 5. Okay. Step number 5. Our test statistic T star is 2.72. It's a positive number, so it obviously does not fall in that negative region, right? It's a positive number. 2.72 does not fall in the critical region. What is the critical region? Negative infinity to negative 1.761. Therefore, I reject. Oops, not I reject. Why am I writing I reject? I do not reject. I do not reject the null hypothesis H naught that mu is equal to 30. Oh, mu is greater than or equal to 30. And that's the whole story. Now, we don't do the p-value here, p-value calculation, but you can use, you can apply similar argument that we did for the other ones, okay? For t distribution as well. Your t is somewhere here, right? So t is 2.11. So since you're doing left tail test, you have to consider all the area to the left of this point, which is obviously bigger than 0.05, which starts from right here, okay, from this point, from here. So this whole area is more than additional area compared to 0.05. So all the area to the left of 2.11 is obviously bigger than all the area to the left of negative 1.761. So your p-value is greater than, so if you want to write it down, step 6, p-value is greater than alpha is equal to 0.05. Okay, therefore I do not greater than or equal to, I do not reject null hypothesis, which is mu is greater than or equal to 30. And that's how you will do the entire hypothesis testing for this. Any question, anybody? Any confusion, questions, concern, anything that is not clear? Everybody okay? All right. Next, the same process we are going to do. I think I'm going to do the next 2 problems and give you a break for the day. It's the same process. Everything is the same. There should be plenty of work for you. And by the way, I did put homework online involving hypothesis testing, and I sent an email to everybody. That was on Friday. So you have a new set of homework online on hypothesis testing. Please make sure to work on those and make sure that you understand how to solve those problems, because that'll give you, I go through the process step by step in the problems, and that should give you an idea of what's going on. Okay, in addition to lectures that where I'm going over all these problems. So now you'd like to know how many hours on the average a student at your school work per week. So you surveyed, or you asked 17 randomly selected students. So your n is equal to 17 and got the following numbers. So we will need x bar and s for these 2 numbers. So we will find it. Assume normality. So you kind of have to assume normality for the population. Otherwise, you cannot apply this t-distribution. If you have a population that is not approximately normally distributed, it's difficult to apply t-distribution. And based on your data collection, can you test the claim that mean number of hours student works is more than 15 hours per week at significance level 0.05. So mu is greater than 15 and alpha is equal to 0.05. Alpha is the significance level, okay? Now, what we are going to do, we are going to go through the process. So first of all, let me find the x bar and x bar and s, okay? So I have the data here. X bar, so this one starts with 15. Okay, I have it here. Okay, L2. So stat calc. Second 2, L2. And I get my x bar 19.88, 19.88. And my standard deviation of the sample is 8.38, 8.38. Okay. Now, step number 1, normality given, okay, in the problem. Step number 2, null hypothesis and alternative hypothesis from the statement of the problem is more than 15 hours. So mu is greater than 15, right? And then this is going to be mu is less than or equal to 15. Mu is greater than 15. or mu is less than or equal to 15. That's what it is. Now, step number 3, to test statistic, T star is going to be x bar minus mu divided by sigma over square root of the sample size. X bar is 19.88 minus mu is 15. All of it divided by, oops, not sigma, sorry, my bad. Remember, we don't have sigma, it's S. S over square root of n. S is 19.8. S is 8.38. 8.38 divided by the sample size square root, which is square root of 17. So on the top, I have 4.88 divided by 8.38 divided by square root of 17. That if I simplify is going to be 4.88 times square root of 17 divided by 8.38. And if I did this calculation, okay, this is what I will get. 17 square root times 4.88 divided by 8.38 is 2.40. So your T star is equal to 2.4. Now step number 4, we are going to do the critical regions, CR, let's call, and we're going to kind of draw a stressed bell-shaped curve, mean 0. So we are doing one tail test with a significance level alpha is equal to 0.05. So we are gonna look at right tail because it's greater than alternative hypothesis. So that's 0.05. And this point we need to find out, and that is going to be this point. And our degrees of freedom, DF, is n minus 1, which is 17 minus 1 is equal to 16. So my degrees of freedom is 16. So I look at the row number 16, and area in one tail has to be 0.05, and area in two tails is going to be 0.10. So 16, area in one tail is 0.05 and area in two tails is 0.10. That's going to give me 1.746. 1.746. So my critical region is actually going to be from here all the way to positive infinity. And if I do the calculation, I mean, write it in the interval notation, it is going to be 1.746 to positive infinity. Now, step number 5, conclusion. All right. My test statistic T star, which is 2.4, it really does not fall in this interval because 2.4 is less than 1.74, right? Oh, sorry, what am I talking? What's happening to me? 2 point, it does fall in the critical region. I was for some reason thinking 1.4, not 2.4. So 2.4 is actually falling in the critical region, right? Because 1.76 is here, 2.4 is somewhere here. So 2.4. It does fall in the critical region. So test statistic T star is equal to 2.4 does fall in the critical region 1.746 to positive infinity. Therefore, I reject the null hypothesis that mu is less than or equal to 15. That means you reject the assumption that average number of hours students work at your institutions is less than 15 hours per week. Now the p-value again, or the probability value method, you can come to the same conclusion. So 0.05 is the area starting from right here all the way to the right. That means technically starting from here all the way to the right. And for 2.4 is going to be all the area to the right of this. Obviously 0.05 contains this area to the right, that is starting from 2.4. Okay. Now, if that is the case, we will have p-value less than alpha is equal to 0.05. Again, therefore, I reject the null hypothesis, right? H naught is that mu is less than or equal to 15. That the number of hours students work is less than or equal to 15. That's the whole story for this problem. Okay. Any question, anybody, before we move to the last problem? All right. So the last problem from this section is this. You would like to know how much money on the average students spend on coffee and snacks at your school per month, not work per month. So is it per month or per week? I forgot. I think I mixed it up. So you asked 13 randomly selected students, that's your N, and got the following data. It's per week, not per month. Assuming normality and based on your data collection, can you test the claim that the average amount of money students spend is greater than $20 per week? Okay, so mu is greater than 20. This is your alpha, and we need to find X bar, and we need to find S for this data set. And once again, I happen to have it in my calculator, so we can quickly do it. So it starts with 50. Huh, I was wrong. I thought I had that data on my calculator, but looks like I don't. Okay, so let's see. Let me go ahead and enter the data into my calculator. Okay, 50, 25, 30. It shouldn't take too long. 50, 25, 30, 15, 29, 35, 15, 29, 35, 30, 25, 33, 30, 25, 33, 26, 15, 26, 15, 31, 40. Okay. I put it on M5, so let's go back to stat, calc, second 5. So my X bar is 29.53. My S sample standard deviation is 9.35. Now we can do the problem. All the steps, step by step. Normality condition given, We are assuming that it is approximately bell-shaped. Step number 2, your null and alternative hypothesis. Alternative, you're testing that mu is greater than 20, right? More than $20 per week. Greater than 20, your null is going to be complement of it. Mu is less than or equal to 20. Step number 3, your test statistic T star is going to be x bar minus mu divided by s over square root of n. So x bar is 29.53 minus mu is 20 divided by standard deviation 9.35. That's the standard deviation divided by square root of the sample size, and you did 13. And it is going to be 9.53 times square root of 13 over 9.35. And if I did that calculation, I should get, so let's see, 13 square root times 9.35 divided by, sorry, 9.53, not 35.
Shouldn't it be 29.53 for your X bar?
X bar is 29.53, yes. I put 29.53 X bar. If you take away 20, it's going to be 9.53. So 29.53 minus 20 is 9.53. And if you did the calculation, you should get 3.67. I rounded it to the 100th place. So your T star is 3.67. Now step number 4, we do the critical regions. So CR, let's call them. And the 0 and our alpha is 0.05, and we are doing right tail test. So this is 0.05, and we need to find this T value. And I am looking at the table, and my DF or degrees of freedom is n minus 1, which is 13 minus 1 is equal to DF is equal to 12. Okay. So 12 and area in one tail, 0.05, two tail, 0.1, it gives me 1.782. 1.782. So your critical region is going to be everything starting from here all the way to positive infinity. And if we put it in the interval notation, it's going to be 1.782 to positive infinity. Now, step number 5, your conclusion. Okay. If you take T star, which is 3.67, so your T star is equal to 3.67. This value does fall in the critical region because look, 3.67 is probably going to be somewhere here, 3.67, right here, somewhere around here. T star falls in the critical region, 1.782 to positive infinity. Therefore, I reject the null hypothesis. Okay. Null hypothesis H naught that mu is less than or equal to 20. That is, students spend less than or equal to $20 on snacks and coffee. Then we could do the same thing using the p-value method. Once again, remember p-value compares the area. P-value compares the area. So it compares the alpha, the area significance level, 0.05, which is all the area to the right of 1.782, and all the area to the right of, to the right of 3.67, that is included in the alpha. That is included in the alpha. So that means area from here to the right is smaller than the area from here to all the way to the right, or all the way to positive infinity. So p-value is greater than, not greater than, less than alpha is equal to 0.05. Hence, I do reject the null hypothesis H naught mu is less than or equal to 20. And that is what the entire process for doing this hypothesis testing. And I hope by now you guys got a very good feeling about this process. It's the very standard process that we do again and again and again for different cases for PMS, proportion, mean, and standard deviation. And that's what it is. Okay, I think you have had enough of information for the day on hypothesis testing. So please go ahead and watch the video, try the homework. And on Wednesday, the next class, we are gonna do the hypothesis testing for population standard deviation. And then that would be the end of hypothesis testing. And after that, what we are gonna do, we are gonna do a couple of things. One is we are gonna do correlation, okay? Correlation between two variables, that's one thing we are gonna do. And we may do a hypothesis testing using correlations. And then the other thing we are gonna do is linear regression. So basically you model a regression line, or you find a best fit line given a set of data. That means you're trying to fit a straight line to a data. That's what you're doing in linear regression. Okay, you have different data sets that kind of looks linear. You try to find a straight line through that data set that best approximates the data set, and based on that modeling, you're going to go ahead and make predictions. So this is more of a predictive statistics, okay? And what we are doing right now is more of an inferential statistics, when you make inference or you make conclusions. So hypothesis testing is inferential, or confidence interval is inferential. However, regression analysis, in this case, linear regression analysis, is predictive. You have data, you come up with a best fit line through that data, and you make prediction using that best fit line or regression line. All right, folks, that's all for the day. Thank you so very much. And you have a wonderful day, and I'll talk to you on Wednesday. Thank you and take care.
Thank you.